Hello everyone, good morning. Welcome to the class 451 Control Engineering. We just studied the Locus. So today we will use Locus to try to design a feedback system with a controller. Alright. Yeah, I will use an example to explain it. Okay. This is ECE451. This lecture is for the 6-week Wednesdays class. Alright. So we design with the control design. By Locus. I use an example to explain it. Suppose we have a plant G of S equal to 1 over S plus 2. Okay, so this gives us a system. Actually, if you just look at G of S without any other things, this one is we have S here, so this is unstable, or it's a marginal stable. Not really stable, right? It's a marginal stable. Yeah, marginal stable. This one, if we give a step response, you check the step response, the step response will go to infinity, because step response give you one more S, step input give you one more S in the denominator, so you have S squared here. The output will have S squared. That give you a T, right? The output will contain T term that will go to infinity. So this is actually this is an unstable system, marginal system. And we want to find the controller, feedback controller. So we need what do we want? We want the feedback system with a controller D of S. It's a unit feedback. All right. Oops. No ink. Maybe the paper part. Anyway, plus minus input the output. Right, we need a D of S, and we want this is the first one with the feedback system. Find the D, right? Secondly, we want of course we want it stable. We want the overall system stable. And the third one, we can have some more requirement, of course, right? Like the overshoot, maximum overshoot, like the setting time, raising time, right? We want some requirement on those. Actually, this kind of things, like MP, the peak value, not peak value, this is the overshoot. Maximum overshoot will be E to the negative pi, right? I have a pi, zeta over square root of zeta minus zeta squared. And the setting time, the peak time, there will be pi over omega n times square root of 1 minus zeta squared. And we also have things like the setting time, there will be a number 4.6 over zeta omega n. This is for 1%. We use 1% as a standard to find the setting time. It should be this. If you change this 1 to be different value, here will be different. And also we have the rise time. There will be some number over omega n. Can't remember. Omega n. Some number. Anyway. Yeah. Some number. Some two something. Yeah, check textbook. Okay, it is approximate. Okay, so you look at it here. Usually you want the peak value small. You want the percentage overshoot small. you want the setting time, rise time, and peak time small. You want this small and all this also small. So you see, you want omega large, right? When omega n large, these three numbers were small. And here, you can see what is MP. This is MP, right? And this is zeta. When zeta is 0, we have 1, right? E to the negative 0 is 1. When zeta equal to 1, when zeta tend to 1, cannot equal to 1. Equal to 1 is 0, right? But when zeta close to 1, this will be a huge number. Limit is infinite. Limit is infinite. No. This one limit will tend to 0. So after you divide it, the limit will be infinite. So e to a negative infinite, that will be 0. So when zeta go to 1, the MP will be tend to be 0. So it will be some curve looks like this, or maybe like this, maybe like this. I'm not so sure. If you are interested, you can just use MATLAB to get the graph of this. Very easy. It's a curve like this. So you see, when zeta increase, MP will decrease, right? So we also want zeta large. So we want zeta larger than something and omega n larger than something. These two numbers depending on your requirement, like maximum overshoot is less than like 20% or 10%, and the saving time in 1 second or half second, something like that. Then you finally from those requirements you can get two requirements on zeta and omega n. Each will be some large number. Like here we can suppose like we want zeta larger than 0.6 and omega n larger than 6, for example. Equal, we can equal is also fine. Alright, so we can have this requirement, and we can also have the first requirement on the on the tracking type. We just suppose keep the same type. Keep the same type with G, but the arrow static arrow, suppose this is smaller than or equal to like point 2, for example. Alright, so we want this. While the input side in S domain is 1 over S to K plus 1. It is 1. Alright, with this kind of input, we want the static arrow no more than 0.2. And we want zeta is larger than 0.6 and omega n is larger than 6, and also want it stable. Okay, so with all these requirements, we try to find the D of S. Alright. Okay, first of all, of course you want to know something about the G, right? What is G? You see the PZ map of G? PZ map of G, we have one is S over S plus 2, right? S times S plus 2 in the denominator. So S, and this is a negative 2. So we have 2 cross 2 poles at these 2 points, and no zeros. This is G, right? G is 1 over S plus 2. This is G. So we have these two. Now the most simple feedback system is this one. If we use D of S, it is just K, right? The proper proportion controller. proportion calculator. We use this one, the most simple one. What will happen? We have a K here, then G here, and we have this one. R is here, Y is here. Right, we have this one. Then we can see the root locus. Actually, if we put K here, we will have same root locus. If we use the function, building function of MATLAB to find the root locus, in MATLAB it is supposed K is here. But you will see K is here or he is here. The denominator of the overall system is same. The denominator is same. They are same. So we have same root locus. Okay, and this root locus we have cross here, so we have two cross, right? Two cross, and then the root locus no zero, so we will have two asymptoters go to infinity, right? Two asymptoters, they go to infinity, so it will be up and down, right? Up 90 degree and down 90 degree. And the center, the point of the center will be these two number, this -2, sorry. The center will be, you add these two number and divide by 2. So it's -1, right? So -1. Okay, so it will be these two numbers. You go this way. So root locus will looks like this. And here will be a breakaway point. If you try to solve it, you will find this center is -1. The break point is also -1. So the final root locus were just like this, like a cross here. It's from 0 to -1, from -2 to -1, and then separate up and down 90 degrees. Yeah, so this is root locus. And we want to find omega. Omega is a Wn, right? The omega n, Wn. Omega n is larger than or equal to 6. So where's that Wn? Okay, we will have these root. Every root we will have this one. This will be Wn, and this will be negative zeta omega n, and this will be square root of 1 minus zeta square times omega n. So it looks like this. So this part should be, we want this is larger than 6, right? Larger than 6, omega n larger than 6. So you start from here, you will try to find the distance here. Suppose this is 6, then you need to choose, you want that Wn, right? Wn larger than 6. Here is a 6. Right? Wn larger than 6 is the shadow area. And you see, then we have to find the K so that the poles located here, right? Located here. This bar will go to infinity. However, what is the zeta? Zeta is, you see, this is omega n. This is a omega n times zeta. So zeta actually equal to, I will say, this length and this length, right? So this length over this length. Oh, okay. If I just say that, this is just the cosine say. Right? It is a cosine say. It's a positive value, and then I put this. Yeah. This angle is this one, right? So it's this one. Zeta is cosine say. Another way is how to say? I say this is alpha, this is a beta. The zeta equal to beta over alpha, right? With a negative. Beta over alpha, right? Beta over alpha. So this one over this, the omega n cancel. You only have zeta. Okay, so here's a zeta over alpha. zeta is the beta over alpha. Beta over alpha. Now beta is 1. Alpha is 6. So this point give us zeta equal to 1/6 and omega n equal to 6. We have this one. And when omega, if you use larger omega, right, you find the poles here, the omega will be larger, but zeta will become smaller. Yeah. And this one is not good. We want zeta larger than 0.6, right? We want larger than 0.6. This one is only 0.1 something, 0.16 something, right? So it's not good. It's not satisfy our requirement. Okay, then what can we do? We use a method. Now we have two Locus. We have in the Locus we have two branches coming up and down, right? We try to move these towards to the negative side. Right? Move these two direction to that side. We move them to the left side, and then we can have more choice on this part, right? On this part. Actually, now we have no choice. This one is 0.1 something. If we want zeta larger than 0.6, so 6 will be 6 should be okay. The unit different already. Sorry, should be somewhere here. We need this one. This is zeta equal to 0.6, for example. Along this line, zeta is 0.6, and we want even larger than 0.6, so we need this part. So you need to pick a pole in this area, but now the whole Locus is outside this area, so we do not have any change, right? Okay, now we try to move these two bars toward this way. So I say this is this is 1. Yeah, that is nothing. This is 1. 2. We use d of s equal to k times s plus z over s plus p. So by this way, we will add one more pole for the whole system. Now the system looks like this. We have a k, we have s plus z over s plus p. Then we go to g. G the same plan. Okay. We use the system looks like this. Y of t. Okay. So now this part is d. This is d of s. D of s. And this one, if we check it by the Locus, this one will be Locus. If you use MATLAB as a function, that will be s plus z over s plus p times g of s. Right? We can run this. Then we can see what will happen. Okay, so g of s already has two poles at 0 and -2. And this one, we have one pole and 1 0. So both are real numbers. Suppose both are the z and p are positive. Suppose z and p are positive. Now we just suppose z, p, they are positive. Then the 0 will be somewhere here, and the pole will be somewhere here. And you can see, after I add this 0 and the pole here, now we have one more 0, one more pole here. We still have two Locus will go to infinity. Right? After we add these, we add a 0, add a pole. So we still have two poles need to go to infinity. So we still have two branch go to infinity. There are two rule lockers will go to rule C will go to infinity, and 2. So the direction is still up and down, 90° up and 90° down. But the center changes. The center changes. Center, the same. Asymptotes. Asymptotes. Center will be -2 plus 0, right? This one plus this one, and we have a p. Negative p is another negative p, right? And plus z, then over 2. It will be this one. So you can see this one will be -1 minus p minus z over 2. If p is large, the center will move this direction towards the negative side, right? If p is small, the center will go to that way, or even go to this side. It's not good, right? So that side will be unstable. So we want p larger than z. So p larger than z, So like some z here and p here, like this. Then what will be rule lockers? The center will be -1 minus this part. So -1 is here. So it will go to somewhere, for example, go to here. This is the center, I say C. This is a C. Then C, we have up and down two directions. And the rule locker will start from, you see, we connect these two and separate up and down symmetrically, like this. And here they just connect like this way. Right. So the rule lockers will look like this, and we can choose, right? For example, here you can choose some value here or here. This one, because the line runs from here to here, so that means we can use same omega n but a larger theta, right? Then we can see whether we can have the right number here to satisfy our requirement. All right, but of course you need to choose what is the z, what is the p, right? Also you need to find this point. S is what? That is the pole for the k, right? For that k, then you can have a pole S here, right? Yeah. And also here we have a name. Here I use p larger than z. In this case, this S plus z over S plus p is called lead compensation. Compensation. Am I good? Yeah. Lead compensation. Yeah. We call it lead compensation. And actually we have another side. If p is smaller than z, then S plus z over S plus p is called a lag compensation. This kind of things, if we add this kind of things in a controller, you will not change the asymptotes. How many asymptotes? You'll get same number of asymptotes because you add a 0 and a pole, right? Yeah, so you will not give more just single poles, no zeros. So the asymptotes will be same. You will have same number of range go to infinity. Okay, let's use the MATLAB to find the numbers. All right. Yeah, I need some calculation. Okay, yeah, I can have both, right? Yeah, like this way. We have we need a S, okay, and G equal to, as a capital G equal to numerator just 1 over S plus 2. Okay, so I have a plant G, and we can see the Locus G. Yeah, it's just a cross, right? We have two poles. One is here, -2. Another pole is 0, and then up or down go to infinite in the middle. So this is Locus. If you pick a value here, like when you click on it, you can see that point. For example, here I choose 1. K is 1.75. Pole is -1 plus 0.864. Then the damping. Actually, this damping is the 0.7, and overshoot is 2, and the frequency is 1.32. Okay, this frequency, that is omega n. This is omega n. We want the omega n large. Okay, let me change the x-axis. X still from negative. I want this -2, -2 to 1. Okay, -3 to 1. -3 to 1, and y from negative like 20 to positive 20. All right. Hopefully it works. All right. And I want zeta, omega zeta. Now this one zeta is good, but frequency the omega n is too small. I want this frequency is also larger than 6, right? I recall I said it's both. One is 0.6, one is 6. So I need to move up. You see, when I move up, the frequency is changing. It's up. Okay. Here's a 6 dot something. And what is the zeta? The damping rate? Oh, is only 0.157. That is too small. So you cannot make both satisfy. This is zeta. This is omega. Right? Omega large, then zeta small. When even large, you see the zeta even smaller. Okay, now I add the D. D is I want S plus the 0. I choose a 0 outside this -2. I choose -3. All right. So 0 is -3, and the pole is S plus a P. I use a P is what? Just a 10. We can see whether it works. Okay, I use this as a D. This is a lead compensation, and then the whole system. Now the whole system look like this, right? So you need the Locus run this one to see the Locus, right? When K is changing, the poles of the whole system give the Locus. You need to run this function. Okay, so let's run Locus. Now is a D times G, right? D times G. Oh, you see, yeah, we pull this to the left side, right? It's still up and down, but now it's here. Then can we find the requirement? I click on it. Okay, this omega is 12, is large. Damping rate only 0.3, so I move down, then that will increase. Zeta will increase. I want zeta increase until 6. Can we have? Okay, over 6. Okay, now we get it, right? Do you see? Now we have over damping is 0.65, and omega n is 6.23. Okay, so now we have the result. satisfy our requirement. You get it? Yeah, satisfy our requirement. So we can just choose these, and the gain is 50.4. Can I just use 50? If I make it smaller, a little bit smaller, maybe a little bit smaller, then if I use 50, yeah, I think 50 works, right? 50 works. So I can just choose 50. This one I use 50. The gain will be a little bit larger than this, so going up a little bit, then the omega will increase a little bit, and the damping rate will decrease a little bit, so it's fine. So I use 50, I use gain 50, right? A little bit up, too much, so 50, right? Okay, so we can choose these. Alright, so we can choose, let me write it. So we choose z equal to 3, z equal to 3, p equal to 10, right? P is 10, right? Z is 3, P is 10, yeah. Z is 3, P is 10, and K is 50. We choose these. And this case, then we have the D times G of S or equal to K and K. This will be, this is the loop, the gain on the loop, right? The gain on the loop. This one we have K is 50, and this is S plus 3, S plus 10, and G itself is 1 over S and S plus 2. Alright, so we have this one. And this case, the T of S, which will be KDG over 1 plus KDG. Right. So what are the PZ map of these? Pole and zeros of these? We can find, just use this one. You can also calculate, but here we can just use a PZ map. You can see PZ map of T. T will be K is 50. K is 50 times D times G over 1 plus 50 times D times G. Okay, this one, right? This gives us something wrong. I need one more. This one. I type. Oh, that is a. Sorry, this is times. It's good. PZ map is here. Alright. PZ map. Oh, some part of the cancel. Okay, it should be. This is the PZ map of the whole system, right? Whole system. This one should be canceled. Yeah, this is a 1 0 1 cross here. They cancel, and this one is also canceled. Oh, they cannot. The system cannot do the cancellation. Like, let me see. What is the transfer function of these? The system gave us with transfer function with order 6 in the denominator and order 4 in the numerator. But actually this one, we know G is the second order and D is the first order, so at most it will be a third order, right? Order 3. So this is, yeah, because the MATLAB just calculated as this way. They cannot cancel. Okay. So we should have 3 poles. Yeah, just this one. Here's one, here's one, here's one. Right? All the 3, we have 3 poles, like here. We have these 3. And here are 3 more poles. They should be cancelled by zeros. And 1 0 is still here. Right? 0, -3. Okay, this one will be good. And these 3 poles, one is a real number, and one is here. You see, the damping rate is 0.653, and the frequency omega is 6.16. Okay, so we have this one. K is 50, then K is 50, D is given above, and we have the zeta equal to 0.653 and omega n is 6.116. Okay, yeah, this one. So you see, satisfy our requirement, right? We want larger than 0.6, one is larger than 6. So we get our result. The thing is, we just pulled it. We pulled these 2 Locus. Yeah, the up and down 2 losses go to infinite. Now I pull them to the left side by add these lead compensation. If we add another way, we add a lag compensation. It will pull it to the right side. If D is, I use D, different D. I use like this is a 13, for example, and this one is a 2. Now this is a we call this a lag compensation. If I add this as a controller, then the Locus, you can see, they push it to that side, right? You push it to the right side. From left side, it push it to the other side. So, for large K, the system were unstable. Yeah. So usually people were. It depends. Maybe some cases you still need this, but in this example, we don't want it. Right? Okay. So now we have the result. Already satisfied the requirement on the zeta and omega n, right? But we have one more requirement. We want the system to be. We want to keep the type. Okay. So this is which part? We have second one, right? Second one. This is actually this third one. Actually stable. This is stable because you see the Locus, all the Locus part in the left side. So it is stable. This requirement already have. So now we check the tracking type. Okay. So this is the third part for the tracking type. So the first one we can check G. If we only have G, this one, the tracking type is G is this one. G is 1 over S plus 1. Okay, so this is type 1. Right? Remember, we have problem in the homework. Then you should know if G is S times something in the denominator, the power of S is 1, then it's type 1. If the power is 2, here will be type 2. And in this case, you use a constant S times it. That means you remove the S part. For this kind of G of S, you remove the G. Remove the S from G. Let S tend to be 0. You will have a constant K. Then 1 over that K, there will be steady state error. And in this case, okay, tracking type is this one. And that K, okay, this is just one S. We call this a velocity constant, kV, velocity constant, velocity, city, C-I-T-Y, city, velocity constant, all right, constant, S or I, S-E, anyway, constant, velocity constant. Velocity constant is limit s tend to be 0. Here's s times g of s. So this is 1, right? We have velocity constant is 1. And steady state arrow, where equal to 1 over kV is 1 when input is 1, there will be just t. And just t. Type 1. So the power of input, you use t as input. T as input. If input is t, then you have steady state arrow will be 1. So this is g of s. And we want to keep this, but we want this steady state arrow to be smaller. Smaller to be 0.2, I think I said. 0.2, right? We want this smaller than 0.2. Now is 1. So we want to reduce it. And we already have now we already have this. We already have d of s, which is a 50 over over s plus 10, and here's s plus 3, right? We already have d of s, so the system looks like this. D of s, which is that one, and then g of s, right? We already have these. So the type, you will check this one, check the type of this, so you need the gain of this part. This part is ds times g of s equal to s plus 10 times s times s plus 2. This part is g, right? This part is d. And the numerator just d, we have 50 times s plus 3. And for g is 1 here. Okay, so d times g, this one. And you see, we have single s here. So it is still type 1. Type 1. And now, what is the steady state arrow? We check the velocity constant. This one will be limit when s tend to be 0, s times d of s, g of s. So this is limit s tend to be 0. Okay, you have s times 50 times s plus 3, s plus 10, s, and s plus 2. You want s tend to be 0. So of course, before you calculate, you need to cancel all the possible s. Cancel as more as you can. Then you let s equal to 0. That will be straight out. Now s cancel. And we will have 50 times 3 in the numerator, and denominator is 10 times 2. So it is 15 over 2, right? It's 7.5. This is kV. And what is the ESS? There will be 1 over 7.5. Oh, we already have certified it. Okay, so if we want more, okay, let me change the problem. All right. Yeah, this example, I just randomly gave some value. This one is already smaller than 0.2, right? What is 1 over 7.5 is 0.13. Is 0.1333 forever. So already set 5.2. Okay, so I change that. I want the steady state arrow smaller than 2%. Okay, even smaller. 2%. Like this. We want this one. Okay, Then compare with these. You see, you compare with this. This is larger than 0.2, right? So we want reduce this. Reduce. How to reduce? You look at here. We do calculate. We need the transfer function here, right? This part d times g, and times s, and then plus sn. We do the calculate. So the final calculation is here. We have 50, right? 50. We have 3. 3 is 0, and 10 is this pole, and 2 is this pole. So we need all these numbers to calculation. We have the k. We want to reduce the static error. We need to increase k, right? Increase k. So how to increase k? If we here have like we have one more, like for example, I put here, if I have this one, then will be 10 times, right? K will be, this one will be 10 times. If I have this one here, will be 10 times. Now of course we don't have it. I just say if I have s plus 10 here, there will be 10 times. So I try to add some 0 here, or if I have s plus 0.01 here, this will also increase, right? You divide by 0.1, that means you times 100 times, right? So you will increase this. So you try to add a pole or add a pole or add a 0 here. Then you can change this. But you cannot just add a 0 or pole. You need to consider 2 more things. The first thing, you don't want to change the rule lockers. Change it too much, right? We already have the rule lockers for that D. After when we add this one, we have rule lockers looks like this, right? Now you add one more pole, one more 0. Maybe this is totally different. Then the previous selection will be not good. We want to keep the previous selection. The same is like you have a plant, you just think you have a real thing, and then you build this one. Okay, you put it here. Then you want to add more things. Not, you don't throw it away. You still need to keep it. You add one more things, make it works. Right? So you need to add one more thing, make it works. You don't want to change too much. So now you add things, and you want to keep it. Of course, you want to keep the rule lockers still looks like this. Okay, we still use compensator. Compensator is what? Compensation. Compensation. A compensation, you will add a 0 and a pole. And that's 1 0, one more 0, one more pole. After you add those two, these two were still going up and down, right? And we know when we add zeros and poles, the center will move. I don't want it to move too much. So we want that zeros and the poles will be some small numbers. Small numbers. If they're large, they will move a lot, right? They're small number or they're close. If those poles and zeros add one more 0 and one more pole, they are close. They are small number. Then these asymptotes up or down, the center will move a little bit, right? Move a little bit. And I also want can make this one like several times. I want like 10 times. I want this change 10 times. Okay, so we can add it like this. Okay, try to add. I say this is lag. Yeah, this opposite with the lead compensation. I use a lag compensation. It is S plus Z over S plus P. Now Z is P small number. I want small number. And when we add this one here, right? That means I will add this part here. Right? I will add this here. After add this, then when you calculate kV, you will have you times Z in the numerator and times P in the denominator. And we want this increase, so you want Z is large, right? Z were large, P were small. So Z large, P small, and both are small. So for example, I can choose, I want this is 10 times, right? I want 10 times it will work. So like S plus 0.001, 01. And here's S plus 0.001. I add this one. Okay, so this one, Z larger than P, and Z over P is 10. Now we have these two features. So this one can increase kV, and yeah, both. Yeah, actually the same thing. Yeah, Z is large and even larger to 10 times, right? Can make the increase kV increase, and also they are small. They both are small number. Okay, then we can see what will happen. Now is, I say this is another D, right? Second D, D2, D2S equal to this, and now the system change to be like this: the D2 and the D and the G, plus and minus. This is D2, D2 equal to this, and the D is 50 times S plus 3 over S plus 10, right? This is a D. Okay, then we want to check the rule Locus, but now we put this, I remove this, I put K here. Then I can choose different K. I want the rule Locus looks similar, and we can choose different K. Maybe same 50K, maybe different K. Okay, now we have a look the rule Locus. Now I need a D2. D2 is S plus 0.01 and over S plus 0.001. Okay, I have D2. Then rule Locus D. Okay, I need a times D2 in front of it. oh, sorry, the D. I changed the D. What is the D now? Yeah, D. I need D. Go back. D equal to numerator should be S plus 3. It should be 10. Okay, this is the D we use. Then rule Locus D2D. Okay, you see this one looks almost same. We add one more zero here, one pole here. It looks same point because one is 1 over 1000, one is 1 over 100, so it looks almost at same point, but actually it is not in the same point. Alright, it's just here, and this part almost the same, and we can choose, we still can choose. You want both zeta is larger than 6 and omega is also larger than 6. I use like 50. Can I use 50? If I still use 50, what will happen? 50? 50, okay, I can use the same 50, you see? Same 50. I still use 50. The damping rate, the zeta will still be 0.6 something, and the frequency omega will still 6 something, right? So I can still use gain 50. So you still use K equal to 50. And then the so we can have zeta is, let me write down, zeta is 0.64 or something, and omega n is 6.62 something. Alright, yeah, I just get this number from this graph. If you want to have the exact value, you can do it as previous step, right? We find this the first time. So now if you want, you can also find it by that way. Here I just copy it. Maybe some arrows, small arrows, just okay. Yeah, it's approximate. Okay, yeah. And then what is the ESS now? Type will be same, right? You D2 times D times G, type is the same, but KV will be different, right? KV equal to what is ESS now? KV will be limit S tend to be 0. Here will be 50 times S plus that 0.01 times S plus, I have first the pole, the 0 at 3, at 2, right? This is at 2, and denominator I have the D2 has S plus 0.001 and D has S plus 10. Am I good? Oh, this is 3. Yeah, this is D. This is D, right? This part is a D. And the G is 1 over S and S plus 2. Okay, now it's good. Right. This is a G. This is a D. This is D1. And this is a K. Okay, so this is again along this way. And here's a unit feedback, so we can calculate KV is S times this. Alright, S and S cancel. Then no more S can be cancelled. Actually, no more S. Then you just let S equal to 0. You have a fraction. Numerator is 50 times 0.01 times 3. And denominator is 0.001 times 10 times 2. So this gives us, okay, this is a, yeah, you see these two are same, right? 0.1 and 0.001 times 10, 0.01. So these two cancel. So I have 150 over 2, which is 75. Alright, then what is the status error? Yeah, this will be smaller than 0.02, right? So we have static error is 1 over KV equal to 1 over 75 is 1 over 75 0.0133, which is smaller than that 2. Smaller than that 2. 0.02, right? Smaller than the 0.02. This is our requirement. Requirement. Yeah, our requirement is this one, 0.02, and the type is still still 1. Okay, type is still 1. Okay, so yeah, this is an example. You try to use the rule Locus to find the controller. Find the controller with your requirement. This is just one example, and in this example, you use the controller just the compensation. Two compensations. I use two compensations. The first is a lead one, another is a lag one, and we got our result, right? That will be fine. Actually, you can have different controller. If you want, you can find different controller. You are still satisfy your requirement. If you want, you can find it. Yeah. Okay. All right. So this is example for the design with rule Locus. And now let's consider another thing. One more thing. So if we consider the. Do we have time? Okay. Yeah. Rule Locus with more parameters. More parameters. The things like we have T of S, which is some, I would say like here's a numerator, doesn't matter what it is. This is a transfer function of the overall system. Yeah. This is a transfer function of the overall system. Right? The output over input equal to this one. Then the denominator, we have some A of S plus K1, B1 of S plus K2, B2 of S, and even more. So like this one. For this one, then we can consider when K1 and K2 both are changing, then where are the poles? Those poles will also give us kind of lockers. But that lockers, you can see, because we have two parameters changing, that lockers will be a kind of two-dimensional things. Yeah, can you imagine? Yeah. If we only have one constant here, k, then that will be just one change. So that will be curve, right? Curve or straight line or curve. So it's one-dimensional, right? If you only have this, it's one-dimensional. But when you have two, then the lockers will move like a two-dimensional. However, we can work like this. You pick K1 fixed, then K2 change, then you have rule lockers. And for different K1, you can have different rule lockers. Then you put them together, you can have kind of you can say root lockers or the net of roots, something like that. Okay. So we can work like this. A, we can consider for each K1, T will be A plus K1B plus K2B, B1, B2. Here's your N, which will be N over A plus K1B. Here's 1 plus K2, B2 over A plus K1B. So you can use if you use MATLAB to do the draw the graph, you can use run rule lockers B2 over A plus K1B. K1 now is a fixed number. You pick a number, right? Each fixed number you pick K1. Yeah, and K1 if you want like a K1 equal to, for example, from 0, then 1, then 2. If you want like a 10 or something, yeah, you can use something like this or some others or the other choice. Yeah, it depends what do you want. Yeah, so you can run this. For every K1 value, you can have these rule lockers. Then you put them together. Right? And the other side for each K2, do same thing. You do same thing. Then you can have rule lockers for you want rule lockers. Okay, you just replace this K1. You change K1 and K2, right? So there are 1 and 2, right? So this is a B1, A plus K2 times B2. Right. You run this. Alright. Yeah, we can use an example to see what will happen. Example. I still use G equal to 1 over S and S plus 1. Now I use like a PD controller. D equal to P is some K1 and D is some K2. D is the derivative, so times S. Okay, so yeah, PD. So the thing is like that. This is a D, this is a G, we have this one. This is r, this is y. Then y over r, the overall transfer function, it will be d times g over 1 plus dg. So d is k1 plus k2s times g is 1 over s and s plus 1. Here's the same, 1 plus k1 plus k2s over 1 over s and s plus 1. So I multiply this denominator on both numerator and denominator. I have k1 plus k2s, and here's s squared plus s, right? S squared plus s, and plus k1 plus k2s. Okay, so you see the thing is like I use this as a of s. This is a b1 of s, which is 1, and b2 s is just s. Okay, then we consider for different k. I use this one, right? For different k, we check the rule Locus looks like this. Okay, let me. This one I think I need a file. I need a file. I have s equal to transfer function of s. I need an s. Then I have as equal to s squared plus s, and b1 or equal to, okay, just 1, and b2 equal to s. It's s. Okay, so I have b1, I have a b1 b2. Then I choose k1 firstly. For I want to put everything in the same figure 1. Hold on. So that means when I print something in this figure, the old thing will not be erased. Okay. Then for k, run from like for 0 by step 1 to 10. I don't know, I just try to see what will happen. I will run rule Locus. B2. I use the first one first, okay? B2. So now k is just b1. So this is a b2 over a plus k. That's just k. Yeah, k1. K times b1. Okay, I run these. And at the same time, I also need to run another rule Locus. Okay, I think k is k2, right? K is k2. K is k2. So I use this one. Right? K is k2 now. K2 now, so it's b1 over a plus k. K now is k2 times b2. Okay. Alright. So for then do I need to do anything? Okay, just run it. F5. F5 is running, and he asked me where I save it. I need to go to it's a desktop 451. Voila. Okay, that one is for the direction of the angle. Now I want the rule Locus with 2 parameter. Just 2. Okay, I know the meaning, right? I just use RL2. Just a name, doesn't matter. Okay. Something wrong in the display. Okay, let me do it again. Maybe I need to close this, I think. Any arrow? This is this one. Anything wrong? Nothing. Okay, so I just run again. Okay, I need to add this one. You see? Okay, all of them I put it together. I don't know which one is which one. So anyway, you see, this is kind of we have a net, right? It is not just Locus. It forms a net. It forms a net. Yeah. When k changes, the zeros and poles is also changing. Locus is also changing. Okay, if I just use one, what happens? So example, I put this one. I just use one. All right. Close off. So I will close old graph. Or is it this one? So for each k, this Locus is like a curve with a line, right? Straight line. These straight lines always have the different curve, half of the circle, right? Half of the circle. And if I move to another side, okay. Oh, just a straight line. Okay, so this case is it is always a cross, right? 2 poles left and right, and 1 bar up and down to infinity. And that one gave us a curve. So we put it together. We will have things look like this, right? Okay, so put it together. We're saying things will look like this. And then if you want to choose some, for example, you want to choose this point. Then you can find what is K1, what is K2, or some point somewhere, maybe if you want to choose some better, for example, you still want zeta and omega, zeta larger than 0.6 and omega is larger than 6. What is omega here? I see. This omega is 3. If I want omega is 6, it's omega is 6, right? This point is omega 6. Omega 6 will be larger than 6. You will have a circle. Use original point as the center, and readers is 6, right? So you need you need this part, the curves more larger. So you need to choose that with more K1 or make more K2s or more K1s, right? You more of those, then you can find this point. Again, try. Now it's 10, right? If I move to 30, what happens? I don't know. 30 curves put on. Oh, still like this. So what is it? I put it here. This is what? Frequency is 0.5, or I even need a more larger. It's 50. Too much. So what is like this point? Frequency omega is 0.7 and damping rate zeta is 0.8. Okay, so this point is good, right? Satisfy our requirement. and you can see what is K1, what is K2 here, what is K1, what is K2 here, right? Yeah, one should be 50. The other, yeah, you take account. If you're interested, you can do it. All right. Okay. That's all for today. Okay, and see you next week. Yeah, see you next week. Bye bye.